Hello everybody. In the last class we discussed about the DC generator. We were discussing about the modeling of the DC generator towards the end of the class. So, we will continue along with that one, finish the modeling of the DC generator, and then we take up a new topic which is the DC motor, which has almost the same construction features of the DC generator, and the operational mechanisms and basic concepts are also very similar to the DC generator. So, we will look at that after we finish the modeling of the DC, dynamic modeling of the DC generator. So, in the last class we had drawn this figure. We have here the DC generator shown as the circle here, to which is connected the brushes, and from the brushes wires are drawn to be connected to the external circuit load RL. There are two non-idealities which are brought out: RA, which represents the armature winding resistance, LA, which is also inbuilt into the coils of the armature, which is the inductive reactance or the inductance of the armature coils. Now, on the mechanical side we have the shaft which is connected to the DC generator, and the shaft is coupled to a prime mover which is giving the energy. So, the energy flows from the prime mover in the mechanical domain, rotational mechanical domain, gets into the magnetic domain, and then from the magnetic domain to the electric domain within the DC generator equipment. The induced EMF EG here is given by this equation which we have seen and discussed in the last class. EG is number of pole pairs into N RPM into phi flux per pole into Z, the total number of conductors in the armature, by 60, a constant. As P, phi, Z and 60 are all constants which for a given motor, EG is proportional to N, or EG is proportional to omega, that is radians per second. The conversion between radians per second and omega would be, if I have N RPM, now N RPM into 2 pi by 60 will give radians per second, or if you have omega in radians per second, if you have to represent it in terms of RPM, into 60 by 2 pi will give you RPM. This is how one goes about converting. Now, EG is proportional to omega, the shaft speed, and it is equal to k omega, where k would be a constant which is fixed for a machine, and that sometimes is given as the nameplate value. Likewise, just as the EG, we said that the DC generator is a gyrator, wherein the EG on one side is linked to the EG, which is a potential variable on one side, that is the electrical side, is linked to the flow variable on the mechanical side. Likewise, the potential variable torque on the mechanical side is linked to the current, load current on the electrical side. So, T is proportional to I, T is equal to K I, the same K into the load current I. So, this is basically the principle of the whole principle of the DC generator in terms of the equivalent circuit. So, we have here basically the DC gen, which is a gyrator. Now, this gyrator has two ports, and the one port is the electrical port as shown here, and this is the generated EMF, and to the electrical port we have the load connected, and this load let us say is RL or R naught. Now, on the mechanical side, there is a coupling of course, and then that is connected to a source, a prime mover, which is going to generate the torque. Now, the load on the electrical side is the load current I, and that gets reflected as the Lorentz force as a torque TL. Now, this is the load torque for the prime mover, which will try to move against the load torque to overcome the load torque, and that would be the generated torque Tg, the prime mover torque, or let us say Tp. We will call this one as Tp, the torque of the prime mover. Now, the shaft has an inertia, reflected inertia, including all the things that are coming from the prime mover side, which is J, and there could be a bearing friction B on one side, that is the mechanical side, and on the electrical side we have LA, which is the armature reactance, which is represented as an inductance LA here, called the armature inductance, which we use for the dynamic model. Steady state model, that is not coming into the picture because it is the DC currents are flowing and it is 0 there, though any voltage induced is 0, and RA the armature winding resistance. So, now we construct a state space model. So, what are the methods of constructing the approach to state space model? First, we identify the dynamic elements. So, dynamic elements are J and LA, and associated with the dynamic elements are the state variable elements. Omega is the state variable element associated with J, I is the state variable element, let us represent the load current instead of a capital I, let me represent it as lowercase I, and then we also have the speed of rotation omega and the I, which is the load current on the electrical side. So, omega and I are the state variables. Now, next we take one dynamic element by after the other and try to construct the dynamic relationship. Now, J is an inductive type dynamic element. So, therefore, we start with J and then let us say LA. LA is also an inductive type dynamic element. Let us take the term the inertial element. So, if it is inductive type, we know that J d flow by dt or d kinetic variable by dt will be equal to the potential variable. So, J d omega by dt, omega is the flow variable on the mechanical side, should be equal to the torque that is produced by the prime mover Tp minus the load torque for the prime mover, which is actually the Lorentz torque, which is coming from reflected from the electrical side. Now, this is equal to Tp, and there is also a friction element which is coming. B, friction is a dissipative element into the flow, which is minus B omega. So, Tp because the Tp, which is the torque that is produced by the prime mover, has to overcome the j d omega by dt, the inertial torque. It should overcome the Lorentz force torque which is reflected from the load. It should overcome the friction torque which is B into omega due to the bearing frictions. So, Tp minus, now TL should be represented in terms of only state variable. So, we have stated right in the beginning at the time of forming state equations that all the variables with which that you form the state equation should be input variables and state variables only. So, Tp is the input variable. Now, TL is the load torque. Now, by gyrator action, the link is K into I. This would be K into I minus B omega. Now, all are in form of state variable. So, this is one equation. Now, the second equation is on the electrical domain side. Again, that is also inductive. LA into d by dt of the flow variable or the kinetic variable, which is I, is equal to, now generated EMF, the generated voltage Eg minus the drop across Ra minus the load voltage. But we have to express everything either in terms of input or state variables. Now, Eg is given by the cross linked variable here, which is k omega. So, you have k omega minus I Ra minus I R naught, all expressed in terms of the state variables. Now, this would give the state equation, which we shall write it as d omega by dt and di by dt, which is equal to, now omega, so minus b by j minus k by j, k by LA minus RA plus R naught by LA. So, you have omega and I plus 1 by j 0 Tp. So, this is the state equation, the dynamic equation, which is of the form x dot is equal to Ax plus Bu. Tp is the input, and of course, we could have an output equation, let us say E naught. Now, E naught is equal to I into R naught. So, therefore, which is equal to 0 R naught omega I, the state vector, plus 0 into Tp, that is y equals Cx plus du. So, this forms the state equation representation of the DC generator, or the mathematical representation DC generator in the state equation form, and this is the dynamic model. So, as we said, in the steady state model, LA will vanish and we just have the resistive drop which comes into the picture. So, with this we complete our discussion on the DC generator. We now go on to the next machine, which is the DC motor. Actually, the DC motor is the reverse of the DC generator. Structurally, the DC motor and the DC generator will look very similar. So, all our discussions on the DC generator can be directly carried forward to the discussions on the DC motor. In fact, all our relationships that we used in the DC generator can also be used, carried forward to the DC motor concepts also. So, our next topic is the DC motor. So, in the DC motor, the black box is still a gyrator. The DC motor also, the black box is a gyrator like in a DC generator. The only difference is that you have the input port, port 1, through which the energy is flowing, energy input is an electrical port, that is an electrical port. And then the other port through which the energy flows out, port 2, is the mechanical port. So, this is the port in the mechanical domain. So, therefore, the variables here are EMF E, voltage E or V, and the current I for the kinetic variable, flow variable. On this side, you have torque and the speed omega. And there is a parameter K, which links the two with the equation T is equal to K I, and the E will be equal to K omega. This would be the gyrator link operation between the two. So, this is the way the DC motor will be used. The same machine, the machine that was designed for the DC generator will act as a DC motor when it is when the energy is applied in reverse. In the case of the DC generator, the shaft is rotated through a prime mover and you get a electrical voltage across the brushes. In the case of the DC motor, we apply a voltage across the electrical brushes and the shaft rotates, giving us the mechanical motion which can be used for driving a prime mover, driving another mechanical load. So, the DC motor also is represented, like in the case of the DC generator, by a circle. So, this is the DC motor, and to the DC motor we have the brushes, and to the brushes we connect the external terminals, and on the mechanical side we have a shaft coming out of the DC motor. The shaft is connected to the armature, and that armature shaft is coupled to whatever the load. Now, like in a DC generator, this wire is basically connected to the brush, and the brush is connected to the commutator segments, and the commutator segments are connected to the coils of the armature, and therefore, the coils of the armature will have a finite resistance, the winding resistance, which we shall represent it as a resistance in series R A, or armature for R A, the armature winding resistance. There is also going to be another element in series LA, the armature winding inductance, which we shall introduce later on while we are discussing the dynamic model of the motor, which will be similar to the dynamic model of the generator. But for most of the discussions that we will be carrying on now, we need the steady state model for which the inductive reactance is not required, because the flow of currents here will be DC, and so also the applied voltage which will be DC. We now have an input which is an applied voltage, and let me call this as EA. So, the voltage that is applied, EA or VA in some of the literature, is applied across the terminals, electrical terminals of the motor. Now, that is going to cause a rotation TG, generated torque from the motor, in this case is the generated torque at the armature shaft. Now, we saw that in the case of the DC generator, due to an external load connected, there was a load current I which was flowing, and the I got reflected back through the magnetic domain and then finally into the mechanical domain as a Lorentz force or the Lorentz torque, against which the prime mover had to force the torque, thereby giving the mechanical energy. Here also, if there is a load connected, now that load gets reflected as a back EMF, in this case will get reflected as a back EMF EB, meaning EA has caused the rotation of the shaft, and because the shaft is rotating, because any shaft in the DC machine, if any shaft in any DC machine, if it rotates, it is going to generate a voltage across the brushes. Though the applied primary voltage has caused the rotation, this rotation of the shaft is going to cause currents to flow through the windings of the armature and produce a EMF across, is going to produce a EMF across the brushes along the same principles that we discussed for the DC generator. Now, this EMF will always be produced irrespective of what causes the rotation of the shaft, and this EMF is called the back EMF because this is applied back, the voltage was applied to make the torque rotated, and this rotating shaft produces a back EMF, and therefore, an EMF which is applied back onto the electrical side, and it is the difference in this voltage which is going to cause, or which is going to get applied across the winding resistance, and which is going to cause the current to flow through this. So, that will cause a current IA, the armature current IA, to flow through the armature. If the speed omega here reduces due to some reason like loading, then this will induce, because reduction in the speed will induce lesser voltage across the coils, because the induced voltage is given by P n phi z by 60. N is the induced EMF is proportional to n, the speed. So, reduction in the speed will cause reduced induced EMF or the reduced back EMF or reduced counter EMF. This is also called counter EMF in some of the literature. And reduction in the EMF here means that there is greater drop across RA, which will force a higher current, which will try to which will try to increase the power which is fed to the machine and thereby make it rotate at the higher speed, bring it back to a higher speed. This EMF is called the back EMF, or also called the counter EMF. Now, IA is given by EA minus EB divided by RA. So, EB is the instantaneous value. Let us put the effective value, the DC values here, because in this case effective value will be the same, EB, and we put also EB here. So, when we talk about the dynamics, we need to put in the instantaneous values in there, and this can also be replaced with the DC value, because we are talking of the steady state. So, that becomes IA, and this becomes also IA. So, IA, the armature current, is given by EA minus EB by RA. It is an interesting relation. What happens at the start? So, let us say you are powering on, the shaft is not rotating, omega is equal to 0. So, you have powered on. At the moment it has powered on, shaft has still not picked up speed, it is starting from 0, omega is equal to 0, and therefore, EB or the back EMF is 0. So, the whole applied voltage is going to come across RA, and therefore, IA will be EA by RA. RA is a very small quantity, because it is only the armature winding resistance. So, IA will be orders of magnitude higher than the rated armature current value of the DC machine or the DC motor. So, initially you will see a very huge current surge due to the fact that there is no back EMF, and then as the current flow in it produces the torque, it starts rotating, the shaft starts rotating, and a speed, finite speed comes into being, which will induce EB, the back EMF, and this back EMF gradually picks up, rises as the speed picks up. And at no load, when there is no load, EB will be a value which is just slightly less than EA, and the differential voltage across RA will be just a few volts, and that divided by RA will be the IA. So, IA, the armature current, will have a very high value at startup and then gradually reduce to a value which is EA minus EB by RA. So, to understand this, let us work out a small example. So, let us say the armature has a resistance of 1 ohm. This is RA. And it generates, now that machine generates 50 volts when the speed is 500 RPM. What it means is, if the machine is used as a generator, it would at its brushes generate 50 volts when the speed is 500 RPM. Now, if the armature is connected to a voltage source EA of 150 volts, then what is starting current? The starting current, the back EMF EB the back EMF when motor rotates at, or should I say, back EMF when the motor rotates at 1000 RPM like this. So, using the relationship that we just saw, that is we saw that IA is equal to EA minus EB by RA. At starting, omega is equal to 0, EB is equal to 0, IA is equal to EA by RA. So, the starting current is given by EA by RA, which is equal to 150 volts by 1 ohms, which is equal to 150 amps. This is 150 amps. Now, the back EMF at 1000 RPM, we have been given that it generates 50 volts when the RPM is 500, and we know that the back EMF is proportional to N. Note that EB is equal to P N phi Z by 60. Back EMF is proportional to N. So, EB1, so therefore, we can say that EB1 by EB2 is equal to N1 by N2, and therefore, if we have 50 volts by EB2, which is equal to 500 RPM by 1000 RPM, and therefore, EB2 is equal to 100 volts. So, now the back EMF at 1000 RPM will be 100 volts. Now, what will be the current at this situation when it is 1000 RPM? The current now would be IA would be EA minus EB by RA, which is 150 volts minus 100 volts divided by 1 ohm, which is equal to 50 amps at 1000 RPM, isn't it? So, this is how one goes about calculating the armature currents, with special importance to be given to the starting currents, because a huge starting current means that the devices that are connected along with should also handle such high starting currents. So, now we need to know the power and the torque relationship. Okay, so we know that the back EMF EB is given by P N phi Z by 60 volts. This is the back EMF. The power drawn from the source. Okay, let us go back and then copy this picture. We will need this picture to have a better understanding. Let us copy that, go to this place here and paste. So, let us have this picture alongside to have a better idea of what we are doing. Now, the power drawn from the primary PA would be EA into IA. So, this is the power, this voltage, terminal voltage into IA will be the power drawn from the primary source, which is the electrical in this case, across the brush terminals. And out of this EA, if we apply Kirchhoff's voltage law here, KVL, EA is equal to the voltage drop across this plus the voltage drop which is across the motor, which is the induced EMF or the back EMF. So, this is equal to EB plus IA RA into IA, or this is equal to EB into IA plus IA square RA. So, the power that is drawn from the source, here, a portion of it, IA square RA, goes off as heat in the resistance, the armature winding resistance RA, and the remaining portion EB IA is the one that goes into the machine. In fact, this is the power. EB IA is the power that is responsible for generating the mechanical power, or the which goes in as the mechanical power. So, the mechanical power actually P M will be EB into IA. This is the mechanical power that goes into the armature. PM is nothing but the mechanical power developed by the motor, EB is the induced EMF, and I is the armature, IA is the armature current. Now, T omega on the mechanical side, if you look at the mechanical side, T and omega are the potential and kinetic variables, and we know that the power is multiplication of the potential kinetic variables. So, therefore, power on the mechanical side is also T Tg, that is the generated torque Tg into omega, Now, this is in Newton meter and this is in radian per second. Let us express the rotation in terms of RPM. So, this becomes Tg into omega is in radians per second. To convert it into RPM, we are making into 60 by 2 pi. Sorry, we normally have the speeds in RPM. What we have is n, because that is the variable that we are using also here, which is in RPM. So, we want to express everything in terms of n, and therefore, n which is in RPM, to convert it into radians per second, we are multiplying it by 2 pi by 60. So, therefore, Tg into n into 2 pi by 60 will give you the power. So, this is in Newton meter, this is in RPM, and this whole together is radian per second. Okay, equating this along with this, we have on one side PM, which is equal to Tg into n into 2 pi by 60, which is also equal to Eb into Ia on the electrical side. This Eb is given by P n phi z Ia by 60. So, we can remove this, we can remove this. So, this would result in the generated torque Tg, which is number of pole pairs, flux per pole, number of conductors, Ia by 2 pi. This is the equation. So, you see that number of pole pairs, phi, z and 2 pi of course is a constant. All these are dependent on the machine parameters, and for a given machine Tg will be proportional to Ia, and also of course the flux, if the flux is constant. Otherwise, we could say Tg is proportional to flux into Ia. So, this is the field and this is the armature current or the load component of the torque. So, this is the field, the flux component of the torque, load component of the torque. Now, let us now take a example to get an idea about the discussion till now about the mechanical power and the torque. A machine has the following details. So, let me write down the details. It is a 225 kilowatt machine, 250 volts, 1200 RPM, DC motor. And some of the details are armature coils, armature coils 243 turns per coil 1, winding type of winding lap winding. There are many other types of windings also, but lap winding is what we discussed in the DC motor generator structure. Same thing is what we are applying. There is also something called the wave winding, but for the purposes of discussion we will limit ourselves to lap winding. Then you have the armature slots, '81, the commutator segments, segments 243, field poles 6, diameter of the armature, armature 559 mm, axial length of armature 235 mm. So, these are the specs of the machine that is given to you. Now, here try to find out, calculate rated armature current, then the number of conductors per slot and flux per pole. These are the things that you need to find out. Okay. So, now let me select this, because we can have this on every page that we copy. Okay. So, now let us try to make a calculation for this. Now, EB is the back EMF, EB is the back EMF, and PM is the mechanical power. IA is equal to PM by EB. Now, 225 kilowatt machine means that the mechanical power that the armature is capable of delivering is 225 kilowatts, which is 225 kilowatts, 1 2 3 zeros, divided by 250 volts. 250 volts is the applied voltage EA. So, here we are taking EA or EB is approximately equal to, EB is approximately equal to EA, and therefore, we say it is 250 volts. So, this will result in 900 amps. So, that would be the rated armature current. That would be the first portion of the problem. Now, let us take the second portion of the problem. So, we have it here so that we can refer back to these values. Now, each coil is made up of 2 conductors, as we saw. Each coil has 2 conductors. So, there are 243 coils, and therefore, 243 into 2 conductors. So, you have 243 coils into 2, which is equal to 486 conductors on the armature. There are armature slots, 81 slots. So, conductors per slot is 486 by 81, which will be 6 conductors per slot, and the coil sides per slot is also 6. The coil sides per slot, and the which is also equal to coil sides per slot is also equal to 6, because there are 6 coil sides in a whole coil. Then the third portion, which is, let us say, the flux per pole that we need to calculate. Let us again paste this. So, the third aspect is to find the flux per pole. So, the motor torque T g is given by, as we saw in the equation here, P by n, that is P m is equal to T g n into 2 pi by 60, and therefore, T g will be equal to P m by n into 60 by 2 pi, which will give you 225 kilowatts. So, 225 kilowatts or 225,000 watts divided by 1200 rpm motor, 1200 rpm into 60 by 2 pi, which is equal to 1790 Newton meter. Now, from the other equation, that is phi, that is we also know that T g is given by P phi z I a by 2 pi. So, phi is given by T g into 2 pi divided by P z I a, which is equal to 2 pi into 1719 Newton meter divided by total number of conductors is 486 and I a is 900. And there are 6 field poles. So, if we calculate it with 1, that is P is equal to 1, this will be 25.7 milliweber. If there are 6 field poles, which means there are 3 pole pairs, and therefore, flux. So, this is flux per pole. This is the flux, and the flux per pole would be by 3 pole pairs for P, that is this one, which is approximately 8 milliwebers. So, this is how one goes about calculating the various parameters of the DC motor. Must have given you an idea about the usage of the equations. Now, the DC motor itself is classified again based on the type of excitation, how we give the flux as shunt motor, we have the series motor, and we have the compound motor. Each type of this motor classification, the name in itself indicates the type of excitation that you would give to generate the flux. So, in the shunt motor, the field coil is connected in shunt across the applied voltage. The series motor, the field coil is connected in series, wherein the armature current IA flows along the field coil, and the compound motor is a combination of the two, which has both series and the shunt connection. A part of the, there is a series coil which connects in series with the armature coils, and a shunt coil which connects across the terminal voltage. It has, there are various advantages, there is the benefits and disadvantages of each of these. We will have a look at these in the next class, in the next session. Each have their own torque speed, their own unusual or unique torque speed characteristics, which are useful for certain applications, and thereby we try to use a particular type of motor for a particular type of application, because the torque speed curve gives an idea of whether that particular motor can handle the load. See, the generated torque speed curve and the load torque speed curve will give you an idea of which type of motor can be used for a given application. So, one point here before we close for this session, we close this session, is about the speed. So, we have here EB, which is equal to P N phi Z by 60. Now, M of course is given by 60 into EB divided by P phi Z. This would be the speed of rotation. So, we use this equation to obtain the speed of rotation of the given motor. But now then, EB is the back EMF, and the back EMF is generally not measurable because the armature resistance is distributed in the armature coil. EB is actually P phi Z is actually E A minus I A R A. So, this would be the exact speed that one obtains in a DC motor for a given applied voltage. In many cases, we can approximate as this drop will be low at higher speeds, because at higher speeds IA is higher for a given power. For a given power, as the speed increases, the back EMF is going to be higher, and therefore, IA will be, the armature current will be lower, and RA is already low, and therefore, IA or RA drop at higher speeds will be negligible compared to the applied voltage, and therefore, this will approximately be equal to 60 applied voltage by P phi Z, where Z is the total number of armature conductors, phi is the flux per pole, P is the number of pole pairs. And this is the speed equations in RPM. With this, let us stop the discussion about the DC motor at this point and continue further and consolidate our concepts with the new topics on DC motors in the next session. Thank you for now.